Hi, in this video we will prove and show that the limit of sine x over x as x approaches to 0 is equal to 1. This limit is a very important limit. Later we will see that using this limit we can find the derivative of all trigonometric functions, and this will be an application, a nice application of squeeze theorem. So first thing to note here is that the limit, if you find numerator and denominator is the limit of each one is 0, and so we are in 0 over 0 indeterminate form. And the regular tricks that we know, finding the vanishing factor and canceling, wouldn't work here. Yes, so we need something new, bring in something nice. Okay, first we will consider the limit of sine x over x as x approaches to 0 plus equals to 1. And for that, well, since x is a small number, so we can form this triangle, right triangle here in the first quadrant. While we're assuming that the hypotenuse is 1, and while in that case, if the angle is x here, then this will be sine x, and this will be cosine x. Okay? But I want to bring in two more things, two more geometric objects, which are sectors of two circles. This big one is a sector of a circle radius 1. The small one is sector of circle of radius cosine x with the angle x, central angle x, both of them. And as you can see, the small sector, which I draw this right triangle so that it shows where it stands, this guy. If I compare it to the triangle itself, since it is inside triangle, the area of that guy is going to be less than area of this triangle. And the area of the bigger sector, or the sector of the circle with larger radius, is going to have a bigger area. So this guy, the area of these three, we can compare easily. Yes, this guy is going to be like that. Well, let's just say equal. And we have all the information here. This is the radius is cosine x, and the central angle is x. So the area of this sector is going to be, remember, half of theta r squared. So it will be half of x, r here is cosine x squared. This guy is right triangle, and we have a height sine x and base cosine x. It will be half of sine x times cosine x. And well, for this other one, we have the information here. So this radius is 1, the angle is theta, half of angle radius is squared. And obviously the areas have this relation. Okay, let's simplify and turn it such that the middle one is sine x over x. In other words, we divide, we get rid of, let me do blue ones, we get rid of halves. We divide all three times by cosine x, so we will end up with x cosine x. So divide everything by x cosine x. So we will have, well, everything cancel out on the right hand side, we will have this guy. In the left hand side, on the middle side, we'll have sine x over x, and on the right we will have 1 over cosine x. And this is true for all x's bigger than 0 and, well, less than pi over 2. We need to be close to 0. We don't need to go that far from 0. Okay, now note that limit of left hand side as x goes to 0, this is continuous function, so it will be cosine of 0, which is 1. Limit of the larger function, greater function, it is again continuous function at 0, so it will be 1 over cosine 0, which is 1 over 1, and that's 1. Left function and the right function, lower function and upper function, have the same limits, and then the squeeze theorem comes in. And what it says that since the limit of upper one and lower one as x goes to 0, well, I was allowed to put only plus, but yeah, this will imply squeeze theorem on one-sided limits, that limit of middle one is also equal to 1. Well, that proves what we were looking for, at least for one-sided as x approaches to 0 from positive side. Yes, this is a very nice proof. I like it, and I encourage you to challenge yourself to see if you can find any other proof for this guy. Okay, what will happen for the limit of x approaches to 0 from left? Sine x over x. Here we need a very nice trick that, well, as x approaches to 0 minus, then minus x will approach to 0 plus. Well, let's just do substitution here. Take y to be negative x. So y to be negative x. And then, well, the limit will turn into this, a sine of negative y. Well, everywhere you see x, you put minus x there, yes. And x is negative y. And, well, as x approaches to 0 minus, y is approaching to 0 plus. And then we know that sine is even function, so it means that odd function, the negative comes out, so we will have limit of negative sine y over negative y as y approaches to 0 plus. These two cancel, and we are back to the limit that we just proved. Well, now for with different variable, but doesn't matter. This is the same limit, and this will be equal to 1. Now that limit of sine x as x over x as x approaches to 0 minus is equal to limit of sine x over x as x approaches to 0 from plus, and both of them are equal to 1. Then we can conclude that limit of the function sine x over x as x goes to 0 itself, not one-sided, is equal to 1. And that finishes the proof. We will get back to this limit in 2 different videos, and we will see that this limit has very nice applications in general.